and let us know why you are here with us, what you like and what you dislike of the TMS, if there is anything that we can improve.
Sorry, I'm very bad in English.
There is a rebound. We all speak English like we say in Italian, Swiss cow. I don't know, Anna, why we say that. Don't worry about that. So I think that if you can switch off the microphone, please. Because I think that, I mean, we have English-speaking people, but they are used to our strange language, so don't worry. So would you like to tell us what you think about the TMS, if there is anything that you want to change?
Yeah, the TMS is very interesting because
oh, here, wait, there is Sara here. No, Sara is connecting. Okay, she's coming. Sara.
Hello, I'm sorry.
Hello. What happened? So it's the time zone wrong or what?
Yeah, the email that I received, it was writing 9:30.
Okay, no, it's okay. In any case, don't worry. We were just wasting time trying to talk each other about what they like and what they dislike about the TMS, but we can do it in another occasion. Okay, so switch off the videos and let Sara. Okay. Okay, so we can start a little bit late, but I'm sure that Sara will be very good in keeping the time. Okay, so it's a great pleasure for me to introduce Sara, because Sara is our former student. So she is from Avezzano, from university, studied at the University of L'Aquila, and then she moved to Brazil. Not because she didn't have any possibilities here in Italy, but because she likes Brazil. And this is what they wanted to do in her life. So she graduated in L'Aquila. She got the master's in cellular and molecular biology in 2011 and a PhD in biotechnology in 2015, working in our group. She was a very strong student, very motivated, opinionated, and so very happy to see that she went on. Very important for Sara, she had the opportunity to travel with the Marie Curie Fellowship that was part of a project that was funded by the European Commission called INTERBONE. And with that, she visited Brazil, the Gran Rio University. Sorry, Sara, if I might pronounce this completely wrong. And also she went to Anna University in India, and that was really a strong experience. Okay, so she is an expert in bone cell biology, in vitro 3D models, alternative to the use of animals, laboratory animals. She's expert in biomaterials and the regulation of nanomaterials. After she graduated here, she went to Brazil in the INMetro, right? And university, and working in the so-called NanoReg project work packages. So there was an international project aimed to introduce regulation in safety of materials in nanoscale. She was for a while a postdoctoral fellow in Brazil at the Brazilian Center of Physics Research. Then she became a professor at Gran Rio. She's very young, guys. She was professor there until the November 2021, and now she's assistant professor at the University Federal Rio de Janeiro, Department of Histology and the Institute of Biomedical Sciences. So she came back to the histology field. Okay, and Sara will present a talk on interchange pink and Sara, the floor is yours. You have to share your screen, and please.
Yeah. Let me check if I'm able to share the screen.
Okay, perfect. Thank you.
Just a minute, so that I have some technical problem here.
You could see your screen shared. Try again.
Let me just switch off and switch on again.
It's not a good day today.
No, not at all. It's the Murphy law, I think.
Yeah, exactly.
Ah, my God.
We could see your presentation. Okay, perfect. It works. You can start.
Yeah. Let me just, are you seeing the pointer? Are you seeing the pointer?
Yes.
Yes, yes.
So good morning to everyone. So first, I would like to thank you for the invitation to join your TMS webinar. It is a big pleasure to me to be here to present my seminar about the interchange between the continents, a look at nano-biomaterials from INTERBONE to UFRJ. So my name is Sara Piperni. I was born in Italy. I studied at the University of L'Aquila under the supervision of Professor Teti. And I studied from 2009 to 2015 with bachelor and master and PhD thesis realized with the Professor Teti supervision. My bachelor is on pharmaceutical biotechnology. My master degree is on molecular and cellular biotechnology, and my PhD is on biotechnology. So during my formation, I was awarded with the different scholarship. The first one during my master in the college, and the other two were financed by Marie Curie. I was Marie Curie fellow within the INTERBONE project in India and in Brazil. This project was headed by Professor Teti and allowed me to have a very big experience, international experience in other labs. So then in Brazil, I started to work with the biomaterials, and I was invited to stay to collaborate with some technical projects that was created to create an international arrangement regarding the nanomaterial safety. After this, thanks to this experience, I got a postdoctoral position financed by FAPER, that is a Brazilian financement. And I started to work at the Physical Brazilian Center. Since my dream was to be a professor, after my postdoc, I tried to improve my experience in teaching. So I was at a private university called the Universidade. That was the first university that I visited here in Brazil. And I got a position as a visiting professor and then a permanent professor. I worked in two programs of post-graduation program, Biotrans, that is a translational medicine program, and the odontology program. And here I start to teach and supervise students, and I received my first grant. So I also have the opportunity to participate in a bigger research network involving all the institutions that I'm working with, the CNPq, INMETRO, and CBPF. So in 2021, I was selected to teach histology at the Federal University of Rio de Janeiro. And now from November, I started to teach at UFRJ. UFRJ is the first university that was created in Brazil with a mission to contribute to the scientific, technological, artistic, and cultural advancement of society through its teaching, research, and outreach activity, promoting the formation of the fair, democratic, and egalitarian society. So it was a big pleasure to me to start to work in this university. And our group is located in Health Science Center. Now we are financed by two different grants that financed our research line. So to understand the whole story, you have to know my origin at bone biopathology lab. So here I worked on bone tissue with a very internationally qualified group headed by Professor Teti. In this way, thanks to the experience that I acquired, I had the opportunity to travel in other international labs. And one of these labs was the Brazilian lab. I was supervised by Professor William Zambuzzi and Esther Takamori, that till now are my collaborators in the research. And the project that we collaborate was aimed to understand the different pathway of kinome profile of the cells, bone cells, MCT3T3, plated on plastic or alternatively on hydroxyapatite surfaces. So what we want to see is that the interaction between osteoblast and hydroxyapatite or osteoblast and plastic. And we found a specific intracellular signaling that is a transduction cascade during the early osteoblast adhesion, activating protein involved on cytoskeleton rearrangement and induction of osteoblast differentiation. So these results was published in this journal, Biotechnology and Bioengineering Journal. And for this reason, I start to work with the biomaterials. So I see that the increase in the life expectancy is a reality, and consequently, it will be an increase on investment in research on new biomaterials. We have to consider that in the last 5 years, we had a double of the $1 billion investment on biomaterials, and this is expected to increase more and more in the future. So this is a good research field to be explored. And biomaterials behavior is strongly influenced by the physical chemical properties, and often this depends from material size. So the body tissue are composed on nanostructure, and as demonstrated here in these images that are dental images, micrography from electronic microscope. And for example, the dental enamel is 42 to 200 nanometers. Collagen is 20 to 75 nanometers or 300 nanometers when it forms fibrillar collagen. So as you can see, the body tissue is composed by nanostructure. So the development of nanoscale materials is becoming increasingly attractive. For this reason, our group start to work with nanometric or nanostructured materials with the different objective in different cell lines. And I will try to resume this. Due to my experience with the bone tissue, we started to work with the two excellent bio bone substitutes that are titanium dioxide and hydroxyapatite. These are interesting material due to the excellent biocompatibility. However, a few data are present in literature about the nanoscale interaction of these materials with the bone cells and its intracellular traffic. So what we are defined as nanomaterials, this definition is going to change. And till now, we consider that biomaterials as the material that have less than 100 nanometer size. But to work in these sites, we had to develop some ultrasound-based protocol, dispersion protocols. And also we are working with the nanostructured materials, because these materials are going to form aggregate and agglomerate. So the nanostructured material is that one that have a particle, the primary particle that is less of 100 nanometers, and it form agglomerate that can be also micro aggregates. So after our dispersion protocol, we first evaluated the titanium dioxide nanoparticle, and we want to see the internalization in osteoblast culture using a focused ion beam microscope. This microscope is almost identical to a scanning electron microscope, but it uses a beam as a beam of ions rather than electrons to energy probe. The advantages is of this extension compared to the scanning electron microscope is that images allow a high spatial resolution, as you can see in this video. So we observed that in 3-day exposition of 100 microgram ml of titanium dioxide in osteoblast, a massive titanium internalization into the cells, and this happened in this vessel. So with the higher magnification, we see that nanoparticles are present into intracellular multivesicular bodies, colocalized with the exosome and cell waste. And we found that titanium nanoparticles can be internalized because they are covered with a rich protein corona that is rich in calcium and phosphate, and that is able to mask the titanium. These findings are published in these 2 papers in scientific reports and nanoscale journal. And then next step was to perform a time-dependent functional mineralization assay in osteoblast culture. So we increasing the dose of titanium dioxide nanoparticle exposure in osteoblast culture, and we found that dose-dependent anticipation of mineralization ability as shown in these images, that is a little in red staining calcium deposition in red. Then we started to work with the 3D cell model to compare what happened in this model compared with the monolayer. So we form a spheroid culture, and then we expose this model to titanium, different titanium concentration. Scanning electron microscope was coupled with the energy dispersive X-ray spectroscopy. And this permit element identification based on atomic structure. So we show that spheroid's morphology is not compromised with the titanium interaction. Then we passed to cut these spheroids to see what happened inside of the cell in the 3D model. And we show titanium nanoparticle internalization in 3D model is also happened in vessel and with the nanoparticle colocalization with exosome in multivesicular bodies. This findings was published in this paper in the scientific report. And then what we are doing now is going to see what happened with the mineralization in monolayer and in 3D model. And we found an increase of mineralization after exposition of higher titanium nanoparticle doses in the 3D model compared with the monolayer. But no significant difference was observed between the 2 models regarding the mineralization in this after low titanium dose exposure. So recently, literature show has the spheroid themselves can be applied in the 3D bioprinting high cell density tissue model. This is an innovative technology for bone repair procedure and soft tissue replacement. What happened is that we are thinking about the combination of a nanostructured titanium dioxide scaffold with the self-spheroid that should be an interesting approach for tissue reconstruction. Second material that our group is working with is the hydroxyapatite. That is an interesting material for bone substitution because hydroxyapatite is actually the mineral component of the bone tissue extracellular matrix. So what we've done is to increase the biocompatibility. We synthesize the hydroxyapatite with the chemical biosubstitution to introduce a carbonate group into the structure. Two hydroxyapatite type could be originated by this substitution. The A type that is originated by a carbonate substitution on hydroxy group, and the B type that is originated by a substitution of carbonate into the phosphate group. Due to the dimension, preferentially B type is formed because the steric ingot of the carbonate is similar of the steric ingot of the phosphate, and this is untrue in this case. Generally, we buy the hydroxyapatite that is commercially available, but this hydroxyapatite is synthesized at very high temperature. So this is different what happens in the human body. And for this reason, we choose a different way, synthesis way. That it is a wet synthesis that allows to work in 3 different temperatures: 90 degrees, 37 degrees, and 5 degrees. And this produces similar material compared to the bone tissue. Electron micrography show that the morphology and the primary particular size is completely different and temperature dependent. So hydroxyapatite that are synthesized in 90 degrees showing a more elongated and probably crystalline molecule because the image seems to be more defined. And this is compared to the other two. To confirm our hypothesis of different crystallinity, we perform X-ray diffraction analysis. X-ray diffraction is based on interference pattern that is caused to the wave present in a X-ray beam. It is incident in an atomic structure of a crystal. So the atomic structure, when the material is a crystal, is uniforming spacing. That's why different materials show different diffractogram as a fingerprint of the materials. So here we can see that the 3 materials analyzed are hydroxyapatite because the peaks is generated at the same angle. Also, more crystalline materials have a more organized atomic spacing, so it will generate a straight peak compared with the amorphous one. The carbonated hydroxyapatite synthesized with different temperatures show diffractogram with different straightness, indicated different crystallinity. And this is temperature dependent, with the carbonated hydroxyapatite synthesized with 90 degrees that present higher crystallinity, confirming the hypothesis that we formulated in the MET images. It is also important to realize the physical-chemical characterization of before and after medium culture contact. So these diffractograms show the pure materials in black line and the materials after medium culture that is represented in the red line. And as you can see in the images, no difference in crystallinity after medium culture exposition was observed. However, we know from the titanium experience that it is possible to have a protein absorption on the material surface. So to check this, we tested the Z potential. That is a technique based on the ionic concentration on the surface of the molecule. And we see the protein absorption on the material surface. This is shown in this graph because the Z potential is decreasing a lot when the hydroxyapatite is in contact with the medium in 24 hours of this contact. So this demonstrates ion absorption. And this characterization is very important to hypothesize that protein corona formed at nanoparticle surface could be responsible for cellular internalization as a Trojan-like Orse mechanism. It's the same that we observed in the titanium dioxide. So this mechanism hides the particle in a layer that is constituted by fetal bovine serum component and ions. After the material characterization, we exposed the bone cell to hydroxyapatite synthesized in different temperature. So we show in these images that are immunofluorescent images, collagen staining, that the 37 degrees hydroxyapatite is able to anticipate and the collagen formation. So it's supposed to be more osteogenic. However, the same hydroxyapatite have different effects in osteoclastogenesis. Acid phosphatase is a marker of micro-osteoclast that is used to verify changes in osteoclastogenesis, osteoclast formation from monocytes. So these assays show monocyte exposed to different hydroxyapatite in osteoclastogenic medium, that is a medium supplemented with osteoclastogenic cytokines to induce osteoclastogenesis. And we show higher size of osteoclast formation in exposition in 90 degrees. So it is a bigger osteoclast formation with more crystalline materials, but higher osteoclast number when monocytes were exposed to the amorphous materials. So these results open the door to a new question that are still investigated in the lab, such as how these nanostructured materials are internalized and processed by bone cells, and how it influences the biological effect on the cells. This question, it will be answered using hydroxyapatite conjugated with rhodamine, that is fluorescent hydroxyapatite, and together with the specific internalization pathway inhibitor and lysosome tracker. Moreover, the hydroxyapatite is a material that is used as a biomaterial in a filler for skin aging prevention. So in collaboration with a startup called High Evolution, we are testing the carbonated hydroxyapatite that we are synthesized with different degrees, and we put it in contact with the fibroblast primary culture to evaluate the biostimulator potential of our materials in fibroblasts. So another different research line is with iron oxide. This is an interesting material for clinic use. This is due to the magnetic properties of iron.
Can you switch off? Excuse me, can you switch off the microphone? Thank you. Go ahead.
So another interesting materials for clinic use is the iron oxide. These magnetic properties of iron particles have the ability to respond to a magnetic field. So this transform the iron dioxide in excellent candidate for magnetic hyperthermia. What is the hyperthermia? Cancer cells are more sensitive to the high temperature, and cancer cells show accelerated metabolism compared with the healthy counterparts. So when we put the cells exposed to magnetic hyperthermia, we expose the cells to the non-invasive cancer treatment techniques that involve the delivery of magnetic materials into the tumor, followed by application of alternating magnetic field. When the magnetic field is applied after iron nanoparticle injection, the tumor cell is selectively destroyed. One of the advantages of magnetic hyperthermia compared with the other hyperthermia techniques, such as the radiotherapy, is that this technique is able to selectively kill the cancer cells with less harming into the surrounding healthy tissue, because the inside-out hyperthermia, in which the higher energy is inside of the tumor when the materials are placed, where the materials are accumulated. So this is pretty different of radiotherapy, for example, that present a mechanism of out-inside hyperthermia with a higher energy radiated in the healthy surrounding tissue. And to do this, we are in collaboration with the Magtech, that is a Brazilian startup, to manufacture iron nanoparticles that give us the particles to test hyperthermia in the for the tumor treatment. And we tested the iron nanoparticle in a 3D spheroid tumor model showing a massive iron internalization with or without membrane around. So moreover, it seems that the outer layer of the cells is able to pass iron nanoparticles to the underlying cells. And after 24 hours exposition, we applied a cumulative magnetic hyperthermia cycles. So we applied 3 cycles in day 1 and additional 1 cycle in day 2. And we observed a considerably progressive reduction in spheroid size. After an additional hyperthermia cycle in the 3D spheroid at the 3rd day, spheroids are completely disintegrated. So next step is to complicate a little bit this model, creating a mixed spheroid with the pro and anti-inflammatory macrophage infiltration. Recent literature show the role of the pro anti-inflammatory macrophages associated with the cancer prognostic. So we plan to obtain these 2 macrophage phenotypes by differentiating THP1 cells on primary cell culture, that it will be activated in the M1 or M2 induction of specific cytokines. We will use the interferon gamma and the LPS to induce the M1 differentiation, and interleukin 4, interleukin 13 to induce the M2 differentiation. So M1, it will be pro-inflammatory macrophage, and M2, it will be anti-inflammatory macrophage. So that cells will be stained with the vital staining and circulating into the microfluidic chip that is creating with the concentration gradient and connected offshore with a pressure flow pump. So we will try to have an immune system tumoral model using different concentration of THP1 cells infiltrating in the spheroidal model. And after this, when we will have the immune system and tumor model, we will validate this model using different iron nanoparticles with a different shape and charge to improve our hyperthermia effect. And these results, we suppose will be promising to create new materials as a new methodology for using alternatively to the use of animals for custom theranostic. This is because the iron particles have the double theranostic, diagnostic and therapeutic field. So finally, I would like to mention our recent work within the Nano Health Nano Network. And in this network, we are involved in a different paper to evaluate nanomaterial safety and contribute with the generation of agreement, that is an international agreement regarding nanomaterial regimen. This is a dangerous flaw in the safety regimen for health solutions. And clearly, all this work is not possible without a research group that's composed by our students and collaborators that I would like to thank, together with the technical and financial support of our microscopy center of Senabio, the Nano Health Network with all the institutions that collaborate in, especially the INMETRO and the Brazilian Center of Physics Research, our international partner from France, and the 2 startups, Magtech and Evolution, for the scientific support. And the last but not the least, I would like to thank my first supervisor, Professor Teti, for teaching me how to do science, how to write a good project, and how to build your good network regardless of which country and condition you are. Thank you for your attention.
Thank you, Sara. So this last picture is the best that we had because we were coming back from India. So we were happy to have some Parmigiano cheese left for surviving. Okay, so I would like to start the discussion now, and then I have some comments. So I saw Marco rising.
Oh, it was just an applause, but I do have questions.
Okay.
So, first of all, hi, Sara. So I hope you, I see you're doing very well. So I'm happy to see that and to see you again. And so I was just wondering, did you try 3D printing these nanomaterials with one of those new techniques they're using, like deposition modeling or laser sintering, something like this?
So we have two research line with the printing materials. You have to see that to print biomaterials, we need the higher temperature. So it is impossible to put the cells inside of a normal 3D printing. But it is possible to construct the scaffold with this one. But what we are going to do is go to the bioprint. We know that it is possible to do bioprint with all the laser deposition or drop deposition. All this is possible. But our problem, we have an engineering problem and a biological problem. The engineering one is to reduce the dimension of the bioprinter, because you can imagine a dentist using like a pen that is able to bioprint cells and collagen and matrigel and hydroxyapatite. But this is a very futuristic opportunity. And the biological problem is the medium in which these cells is able to live, be healthy, to be bioprinted. And what the literature show is that the one cells is not enough to conserve the healthy of bioimpression. So this why the spheroids, it will be interesting. And this why the nanomaterials is interesting if they are able to simulate extracellular matrix, give growth factor and these things in a bioprint intention.
Thank you.
Oh, that's very nice. Thank you.
Other questions, Marco? Okay. Any other question from the audience? Don't be shy. Sara is one of us. Sara, I have a question related to the internalization of the biomaterial that affect bone formation. As you know, the osteoblasts induce mineralization of the bone tissue, releasing matrix vesicles that certainly are one of the many categories of the extracellular vesicles, but these are very special because they induce the precipitation of the hydroxyapatite crystals. Now, are they affected by the biomaterial? So the biomaterial is internalized, but is in some way elaborated and say resecreted, or does it change the rate of generation of matrix vesicles or these type of things?
Yeah, so this is different in the two materials that we are working with. Titanium is a metal. So what happens is that cells is not good with the metal inside of them. So it's a dose-dependent question, but it's also, that's why this research line started, because we was thinking another things. We was thinking, okay, you put the metal in dental implants, and then these implants release these particles. So this is crazy in the bone environment. But we found another things. So it's good because it is osteogenic. So this is pretty tough because we don't know what happened inside of the cells. Of sure, we are analyzing what happened with this exosome, because if are colocalized with titanium, for sure, this response is influenced the other cells around. And this is with the metal one. Hydroxyapatite is the mineral component of bone. So for sure, the osteoblasts like to eat hydroxyapatite. And what happens is that they are able to reprocess this hydroxyapatite in tiny crystal.
Mm.
But what we are going to see now is if it is dependent from the temperature, crystallinity. So what's happening, for example, 21 days, because we have these results with 24 hours or at least 3 days. So in 1 day, what happened with this vessel? So it is this hydroxyapatite that we are putting in that are reprocessed and go outside, and it should be internalized again, go in the lysosome. We don't know.
Okay, so you have things to investigate in the future.
Yeah.
But it's interesting from a biological point of view, because the first step to induce the formation of the first crystals is quite a tough step for the osteoblast. And then these attract other crystals. So maybe it's a step forward. So the vesicle start a step forward, and this could be something that can stimulate.
Actually, with hydroxyapatite, I had some picture from electronic microscopy that show how a structure that is similar to lysosome. Mm-hmm. So my sensation is that the hydroxyapatite, it will be colocalized with this lysosome, and we know that lysosomes are involved in osteoblast mineralization. So I think this is the mechanism. Throw the lysosome to put extracellular vessels and start again or improve the mineralization.
Well, there is one thing that could be against this, because the lysosomes have a low pH and the hydroxyapatite is dissolved in low pH. So something that you should consider. But it's really fascinating. Another just comment or curiosity. I remember when Suellen was in our lab that she was working with the hydroxyapatite prepared at different temperature to correct the critical defects. Are you collaborating with her? Or there is any?
Yeah, we started from the same material, but he was working with the macrosphere.
Oh, okay. With big difference, yes.
And actually, we have a good results in vivo with this macrosphere with the 37 degrees hydroxyapatite, and we don't know why. Yeah. So that's why I started from that, and then I continued.
Okay. We have a question from Hannah. Hannah, unmute yourself. You can speak English, I think.
Okay. I was just thinking, because you were talking about nanomaterials and nanoparticles. In Manchester, we've got a huge graphene research institute, which is a nanomaterial, and I wanted to know kind of if you think that, what's your opinion on graphene as a nanomaterial, and if you think that there's some specific biological application?
Yeah, for cancer therapy especially.
Okay.
We have 2 collaborators that works with the graphene. One is for diagnostic, graphene quantum dots are interesting for diagnostic. And another one is related to the cancer therapy, because they put radioactivity in the graphene. It is a radiographene conjugated. But also we put the radioactivity into the hydroxyapatite. It is working well than graphene.
Oh, okay.
we just have the problem, so we still not have the solution.
Okay.
Okay.
Any other questions?
Not
from the audience? Not from you, Hannah. What about the other people in the audience? Don't be shy. You can write the question, or you can, Michela.
Hello.
I have a general question regarding the your career or our career, let's say, because I'm a young researcher. I don't know if you have some advice for us, maybe how to move inside, you know, the first steps in science, since you are experienced and also quite, your career is very impressive. So I don't know if you have some general suggestion for us.
I have one. So you have to listen on what happened around you. I learned how to do some of these things that helped me till now, just observing Professor Teti doing it. I'm a leader now, so I'm responsible to put the money into the lab. This is something that in the Professor Teti lab, I'd never be worried because she do this for us. It's just you have leaders around you, and you just have to observe how they are moving in a congress, how they are writing project, how they are supervising you and other people, what is good and what is not good, and also have the feeling regarding what is good and what is wrong, because we know that university is a complicated environment, and some people are there and doing nothing, and some people are there doing everything. So it just feel, you know how to feel this. It's a human behavior.
Thank you.
Other questions? If not, I'd like to take this opportunity, Sara, to say something that is very important for this audience. This audience is done by young people. Most of them are students or just graduated or PhD students, and they all have the problems that you were mentioning. But I want everybody to know, first of all, that I'm very, very, very proud of Sara for many, many reasons. She came into the lab immediately after or immediately before the earthquake. We never stopped, right, Sara?
Right.
We were strong and we carried on. And the first part of his training was not easy at all. I made mistakes, but then we realized together, and here is Sara. Important features that I see really in Sara, but not in many of the young people around me, is that you have clear ideas on what you wanted to do. And for this, you found your path. So you decided that you wanted to go to Brazil, if you wanted to be professor there, and all your career moved in that direction. And this is unique, I would say, more than rare nowadays. So I really would like to encourage people to think about having clear ideas. I cannot hear people that who are now in their 30s say, well, I don't know what to do in the future. Another point is that Sara is a strong person, and for this reason, she never gave up. She didn't give up during the earthquake. She didn't give up in the times that were not perfect, and she went on just enjoying what she was doing, which is absolutely important. Don't forget, you have to be paid to have fun, and she has fun with this job. Another important point, Sara, I don't know if you realize that, is what in Italy, an old-fashioned expression is that we together, you and me, we made a school. The school is, in scientific terms, a group of people that train young people, and these young people stay in the field, which doesn't mean that they work on the same topics. In fact, I do not work on nanomaterials. Just I had some collaboration and nothing else. But she is in the bone field. So this means that she learned from this group and she continued in the field, making this school strong and international. And this makes me really very proud. And now it's very difficult to have this. Fortunately, there are still people that do this. But I don't know if I told you already, but I come from a department whose director was Professor Amprino. Professor Amprino was the colleague of Rita Levi-Montalcini, Renato Durbecco, and Salvador Loria, so 3 Nobel laureates. And I feel that I come from that institution. And my mentor was Alberto Zallone, who was the first to identify the method to isolate a large number of osteoclasts. In fact, I work also on other fields in the bone environment. But if people ask me, what are your preferred cells? How would you describe yourself? I say that I'm an osteoclast person, because I feel that that is my school, the osteoclast. And you saw the picture coming back from India. Remember, Sara, when I visited you in India? The environment was so bad, but she didn't complain even 1 single minute. And she found friends there. And she's very tight friend of some people there. So when I saw you, I said, Sara, what I did sending you here. And you were smiling like you are doing now. So Sara is an example for any of you. So I hope that she can share her email address. So if you have any question, any request of suggestions, anything, you can just email Sara. Very proud of you, Sara.
Thank you.
Any question from any of you on this part of young people want to know anything? Well, go ahead.
I would like to thank you again, independent from the presentation, because I feel this staffs of the school. I mean, in the last week, I was in an international meeting with the French people, and they were looking for somebody able to perform osteoclast culture. And I see I can give my students for you. And the other person that worked with me, she was a technician in the lab, and she was helping me to perform the osteoclast culture. So she learned how to do this. And some months after, she was without desemployed. And she went in another lab that was looking for lymphocyte culture, that is the same of osteoclast culture isolating by the barcode. And then she said, I'm able to do this. And see, nobody is able to do osteoclast. That for me is the basic one. It was the technique that I learned.
Yeah, Sara, when we first got the osteoclast, the very first time, Albert and I got the osteoclast, we were working with a strange apparatus in the refrigerator. We were supposed to use a cold room, but we didn't have a cold room, so we did it in the refrigerator. And so when we saw these cells, you know what there was in the refrigerator also? A bottle of champagne. So we ended the night just drinking because we got the osteoclasts.
Yeah.
Okay. And now I want to also say, just to continue your thought on this, that there are people who complain and people who work hard, and these are to real categories. I heard from one person once this phrase, human beings are divided into categories. Who do things and make mistakes, who do nothing and criticize. So Sara, you do things, maybe you make mistakes, but you are in that category and not in the category of those who do nothing and criticize. Okay, so I hope this was a good TMS meeting today, that you learn not only science, top level science, the pictures of the electron microscope were just great, Sara, wonderful. But you also learned something in terms of life and in terms of science. This is something that I really would enjoy if I were one of you. So Sara put her email address in the chat, just you can copy, and let's keep in touch.
Thank you, Professor.
Thank you, Sara. And of course, when you will come to Avezzano, just visit, and maybe we can have a face-to-face meeting with all these guys talking about science.
Sure, I will.
Okay. Bye-bye, and thanks for making it, although you woke up just 10 minutes before.
No, I went in the lab, but I was in the culture room. So. In
the culture room. Okay. Hope that the cultures will not be disrupted by this. No. Okay. Thank you very much, and have fun with your research. Bye-bye.
Thank you. Bye.
Bye.